Hi everyone, this is going to be the pre-lab for the final experiment of the semester. This lab is all about titrations, and titrations are a very useful tool in chemistry. If you take any further chemistry courses, you will see titrations, again, just because they are such a powerful tool. And the reason they're a powerful tool is they allow us to solve for an unknown amount of something. In acid base reaction, we can usually find out how many moles of an acid or a base we have, and by that we can tell the concentration of it. And the reason that works is based off the chemistry. So we've seen this before. So a general example of this would be if we had HCl and we reacted it with sodium hydroxide. We know all acid bases react and form water and a salt. These reactions are very efficient. They usually occur at near 100%, which is very good for us because it allows us to very specifically tell the amount of each chemical we're using, and that allows us to calculate the unknown quantity of the other. So, for example, a classic example you would get is it would ask for the concentration of one of these. You would start with the concentration of one, and you'd be asked to solve for the concentration in the other. So, for this example, we'll say we have 0.25 molar sodium hydroxide, and we're going to say we used 35 mils of it. And we titrated with 35 mils until we reach what's called an endpoint. You can tell your endpoints by your indicators. I'll get to that in a couple minutes. So when we got to the endpoint, we recorded 35 mils of sodium hydroxide being used. What we reacted it with was 15 mils of an unknown concentration of HCl. The question is going to be, what is the concentration of this guy? So this sounds like it's going to be a lot, but it really isn't. It's the same things we've been doing the last couple of weeks. It's the same kind of conversions. It's just seeing it in a different light. So really the only big equation we're going to need is what we've been using the last couple of weeks, which is the fact that molarity is equal to moles per liter. So you guys can see for the sodium hydroxide, we have a concentration. We have a volume, which means we know how to solve for moles. If we look at our equation above, everything's a 1-to-1 molar ratio. So for every mole of sodium hydroxide I use, it means we're going to use a mole of HCl. So once I calculate moles of sodium hydroxide, it allows me to very easily get moles of HCl that were there. Once we have moles of that, we also have a volume of HCl to start. So we're going to calculate our moles based off the sodium hydroxide, which is going to tell us how many moles of hydrochloric acid we have. The volume is given in the problem, so we're able to calculate molarity. Guys, this is a very useful habit to get into when you're doing chemistry problems. The more complicated they get, the more it's going to be helpful to write out your givens, see where things are, and see how you can convert to a point. Basically, set up a game plan that you're going to use for the problem. So the way we'd get through this is the first step, we got to calculate the amount of moles of sodium hydroxide we used. So 0.25 moles times, it's going to be the volume. We used 35 mils. If I convert that to liters, that's going to be 0.035 liters. And if I punch that into the calculator, we're going to get 0.00875 moles. We know because of our equation that for every 1 mole of sodium hydroxide, we're going to use 1 mole HCl. So that means that by calculating the moles of sodium hydroxide, I also calculate the moles of HCl. This isn't always the case. The molar ratios aren't always 1-to-1-to-1. In this case, they are for the example. You guys are going to see in a little bit the way the experiment's set up, it's not 1-to-1. So now that I have moles, next step is to calculate the concentration of HCl. So we had 15 mils of HCl to start. So all I'm going to do is say that molarity is equal to moles per liter. And I'm going to substitute my units in. So moles, we have 0.00875. My volume is 15 mils. Convert that to liters, it's 0.015. And if we punch this into a calculator, what you guys are going to see is my starting concentration of HCl was 0.58 molar. So this is how titration problems are usually set up and how you usually get through them. You guys are going to see that this lab is a little different. We actually have starting concentrations for both the acid and the base in this one. We're going to be actually looking for something using the same kind of chemistry here. We're actually going to be looking for a different answer, which is really cool. But in order to better understand that, we have to first go over what the indicators we're going to be using are. So indicators are chemicals that we use in the lab that tell us the pH of a solution. They don't actually interfere with the reaction going on. They just let us know via a color change what is going on. So this right here is an example of an indicator. This is phenolphthalein. Phenolphthalein is a indicator that goes from colorless in acidic solutions to a bright pink in basic solutions. So what you guys can see here in the cartoon is kind of just an example of what phenolphthalein looks like when you're titrating it. So when you're in acidic solutions, you can't even tell that it's there. When you start adding base to it, it starts becoming pink. And ideally, when we're in lab, we want this to be a very, very faint pink. What usually happens is when you add more base to it, because that solution is basic, you'll see the solution turn pink when it hits the solution with the indicator in it. That color will quickly fade away. What we want when we're doing the experiment is that color to stay around, but we don't want it to be what I usually call highlighter pink. So this right here would be what we would call an over titration. When you have too much of the base in there, it's going to look very, very bright pink. When you hit an endpoint, it's almost going to look colorless. The best way to tell with phenolphthalein at its endpoint is to hold it up against a white background. Then you can just barely see the color, and then that is the perfect endpoint. And the reason we want this to be a really good endpoint is because if we over titrate, you guys can see based off the example I just did, it's going to mess your whole calculation up, and you're not going to get a direct relation between the two because you'll have excess of that other one and you'll be calculating too much for that initial volume. So the last thing that's important to note here, guys, about phenolphthalein is the fact that this color change occurs around pH 8. Different indicators will change color at different pHs. This is the pH range that phenolphthalein will change color in. The other indicator in the experiment is bromocressyl green. Bromocressyl green changes color at 3.8 to 5 pH. And this is a little more of a tricky indicator to work with. You guys can see here based off this picture I got off Google. The color range is a little more different. There's a bit of a more drastic range. But if you guys look at this little number line like thing here, the endpoint for this one is a very narrow band in this. And this picture does it really, really good job at showing the color. In practice, the difference between the acidic solution to the endpoint is very subtle, especially if you don't have enough indicator in the solution. And this indicator specifically is very easy to over titrate into the blue. And once you're into this color, you know that you've overshot your titration. And sometimes you don't even see, you'll just kind of go right by this without realizing it. So these guys right here are the proper endpoint. The very last thing I want to go over before we get to the actual experiment is the burette. So this would be the apparatus you guys would be using if we were in lab. And basically all the burette is a very accurate way of measuring and dispensing volumes. So you guys can see along the side here, the graduations start at 0 at the top here and go down to a certain amount, 50 here. And these are very, very fine graduations in real life. This cartoon of it only shows like 1 mil increments. The ones in lab have increments to a tenth of a mil each, and then you can estimate between the 2 tenths of a mil to get very accurate readings. So the way this works, your lab book kind of goes over it too, is you turn the valve here so that it's parallel with the burette. That'll dispense. When it's perpendicular, it stops, and you can control the flow rate out of it very precisely. You can get it so that it's just dispensing a drop at a time, and that's often how you titrate towards the end. When you start getting really close to the end point, you're going to see that your indicator color sticks around a little bit. For the phenolphthalein example, going from colorless to pink, you'll basically see the drop sit there for a little bit, and that color will stick around, and then it'll very slowly fade away. When you get to that point of the titration, that's when you start going drop wise or even half drop wise. You can hang a drop at the very tip of the burette here and then wash it in with water. That is often the best way to get to your endpoint without over titrating. So on to the experiment itself. The reason I said that this one is a little different is because we are using phosphoric acid and we know the starting concentration of it. So you may be asking, if we know the starting concentration of it, why are we even doing this? Well, phosphoric acid has multiple what we call acidic protons. You guys can see phosphoric acid, H3PO4. Each of those H's or protons, so you're going to hear me interchange those terms because a hydrogen ion is just a proton. If you guys look at the periodic table, the molecular weight of hydrogen is 1. The atomic number is 1, which means most of hydrogen is a single proton with 1 electron around it. So if I make it an ion and remove the electron, it's just a proton. So you hear in acid-base chem, people refer to hydrogen or the proton. I'll probably interchange them multiple times within the same sentence. So phosphoric acid in this case actually has 3 protons. And each of these protons are going to pop off at a different pH. You're going to need a different amount of base for each of those to pop off. Thankfully, both indicators we have here both represent a different endpoint in this titration. One of them is going to represent the endpoint for the first proton. One of them will represent the endpoint for the second proton. I'm going to give you guys a hint. We will not be using the third proton. That one is very tough to get off just because it's the last one. You start building up a lot of charge to get that last proton off. So it's mainly just these two that we're going to be dealing with. So the way we're going to be able to tell which indicator is representing which of these two equations is just by the molar ratio between the two. Remember, the amount of base you use is going to be dependent on the acid itself. And you guys can see here that if I'm just measuring the first endpoint, it's 1 mole of phosphoric acid and then 1 mole of sodium hydroxide. So if it's at the first endpoint, my molar ratio between the acid and the base is going to be 1:1. You guys can see if I'm getting that second proton off, the molar ratio goes from 1:1 to 2:1. So it's going to take twice as much base to get that second proton off as it does that first proton. So that's how you can tell which indicator is going to represent which endpoint. And that's what the calculations you guys are going to do from the data that I'm going to give you is going to determine. The very last part of this experiment, part C, is about determining the mass percent of acetic acid in vinegar. If you guys remember from the second to last experiment we did, when we had the glacial acetic acid that we used to turn the light bulb on, I told some of you guys that most of you have been in contact with some form of acetic acid at some point in your life, and that's because acetic acid is found in vinegar. Vinegar is a dilute solution of acetic acid. It's also why that part of the experiment in the lab sort of smelled like someone opened a bottle of vinegar. So thankfully, titrations are very good at determining the amount of an unknown. And we have an unknown in acetic acid. So what we can do is we can solve for the mass percent of acetic acid in vinegar. And the way we're going to do that is we are going to titrate it. So acetic acid, you guys remember, is CH3COOH. You guys are going to see, those of you who go on to organic chemists tend to put their acidic proton at the end. So that's the proton we're going to be worrying about. If we react this with sodium hydroxide, we get our water and our salt. I'm just representing the acetate anion as AC. That's another shorthand. You guys will see the further you get into chemistry. I'm just running out of room here. So we can see here, this is a 1-to-1 ratio. So for every mole of sodium hydroxide we use, we're going to use 1 mole of the acetic acid. So this has a couple extra steps. This is going to be similar to what I went over to start the pre-lab lecture, with a couple extra steps in it. So we're going to have a mass of our unknown, of our vinegar. So we're going to record the mass. We're then going to titrate with sodium hydroxide until we hit our endpoint. When we hit our endpoint, we're going to have a concentration of sodium hydroxide that we know. We're going to have a volume of sodium hydroxide that we titrated. That's going to let us calculate the moles of sodium hydroxide. Once we have the moles of sodium hydroxide, we can say for every 1 mole sodium hydroxide, it's going to equal 1 mole of our acetic acid. Now, for part C, what it's asking is a mass percent. So once we have moles of acetic acid, we're not done yet. We have to get the amount of grams of acetic acid. Because remember, we have that weight from the start of the experiment as well. So I need to convert moles of acetic acid to grams of acetic acid. And you guys know how to do that. It's using the formula that the moles of anything are equal to the grams of it over the molecular weight. We just calculated moles. Molecular weight we get off the periodic table. That gets us to grams. So if we go moles times molecular weight of acetic acid, that will give us grams of acetic acid. Once we have grams of acetic acid, the last thing we have to do to get the mass percent is divide by the grams of vinegar that we had at the beginning. And that will give us our mass percent after you multiply it by 100. The very last thing you guys are going to do for the experiment, for the post lab, is statistics. So if you guys remember from the very first experiment we did with the taking the temperature of the room and measuring the plastic or metal rod, we gathered data together in a table, and then we did statistics on it, a Q-test, and all that stuff. It's the same thing we're going to do for the mass percent of the acetic acid. I'll have a table of those values with the rest of the data as well. So the very last thing you guys need is obviously the data. So this is going to be the data you guys are going to use for the experiment. So for all parts of this experiment, the concentration of the sodium hydroxide is 0.1 molar. That's the base, for those who aren't sure which is which. And the acid is obviously going to be the phosphoric. And the phosphoric for parts A and B, the concentration of that is also going to be 0.1 0.100 molar. So you guys can see here for parts A and B, you have 2 runs each. You're going to take the average between the two. So you guys can see for run A, we're going to use 24.50 mils of the NaOH. And for run 2, we're going to use 22.50, each of which are going to have 10 mils of acid in it. Part B, we're going to have 10 mils of NaOH to start and 10.2 mils in run 2, and again 10 mils of acid to start. For part C, the initial mass of the vinegar is going to be 1.853 grams. The volume of sodium hydroxide we'll use to titrate that is going to be 14.50 mils. And then the percents for the mass percent for vinegar that you guys are going to use for the statistics part are listed below. I'm not going to list those all out. So you're going to use the value that you calculate here and include it with the numbers that are listed below. And with that, that should be all the data you guys need for this experiment. If you guys are comfortable with it, you can go ahead and get your final post lab of the semester done.